Esu Aurelijus Rinkevičius, esu podoktorinis darbuotojas Cornell universitete ir pakalbėsiu apie mūsų ir kolegų tyrimus didžiajam hadronų greitintuve. Tai ar turime kažkokių kalbos pasiūlymų? Do we have language preference?
Whichever you are better with.
For me it's the same. Tai anglų? Okay, I can use English, that's fine. So I'll continue in English then. So, all right, I'll start with the introduction, although the slides will be in Lithuanian, so you can follow this bilingual matter. So, first of all, this is LHC. It's just a schematical picture of the accelerator complex at CERN, where the largest ring is the LHC ring, which is 27 kilometers in circumference. And however, to get there, the particles have to undergo several stages of earlier acceleration. And finally, they reach LHC, and then collisions happen at the experimental points. So, although we've started in 2010, the real data taking can be said that started in 2011. And so 2011 and 2012 were so-called run one of LHC data taking. And then in 2015, after a long shutdown, we continued at higher energy. And I'll say something about that later. So we have collected already 100 inverse femtobarns of data, and that's still growing. And what's interesting is that LHC already delivered higher instantaneous luminosity than the projection. Okay, so this is the detector I'm working with. I've said already there are 4, and this is one of them. And so what's happening here? So we have a beam pipe, so protons or lead ions traveling through the detector, and the collisions are happening at the very heart. It's not just one piece of hardware. It has many different layers, starting inside with a silicon pixel, silicon tracker, electromagnetic crystal, scintillating crystal calorimeter, then hadronic calorimeter, which is plastic scintillators, and finally, at the outer of the solenoid, a superconducting solenoid of 3.8 Tesla, we have a gaseous detectors, 2 types of gaseous detectors here and there, so-called muon system, for exactly this purpose, that most of the stuff gets absorbed here, while only the muons can escape, and of course neutrinos that we don't detect. So, all right, so this machine has to operate at the LHC frequency, which is 40 megahertz, and we have about 27 proton collisions per hertz. So that's quite something. So it translates into about orders of tens of terabits per second. So that's something that we should handle, first of all, like online, so on the fly, and only keep the interesting data on the tape or disks. All right, so this is just an example how the collision would look like if we would like to see it in pictures. So, however, this is not what we analyze. This is just a graphical representation to illustrate what happened. So, before I continue with physics, I want to make a blitz introduction to the particle physics. So, in particle physics, we have standard model. And so standard model is the core of our theory. So we have 3 groups of particles. We have matter, quarks. We have another type of matter, leptons. And then we have gauge particles that are force mediators. And there's a special boson, which is called Higgs boson, and that we have discovered recently. And I'll talk about it later. In particular, I'll talk about two heaviest elementary particles, top quark and Higgs boson, in the later slides. And of course, the remaining piece of the unknown so far, we know that there are at least two forces, two type of interactions, so gravity and dark interactions, dark matter, dark energy, that we still do not understand. All right, so next I'll go to the real contents of this presentation. So the search for the top and Higgs quark direct interaction. All right, so what's the big deal? Why do we care about top and Higgs interactions? So first of all, looking for TT bar Higgs process is the only direct search to investigate the TTH vertex. So why is this important? This is important because if you look at this table here, so it tells you the ways to produce Higgs boson. And we see that most of the time, actually, we produce Higgs bosons by two gluons joining together through the effective vertex and forming a Higgs boson. Now, the thing is that this effective vertex, in theory, should be dominated by top quarks. And dominated, I mean 99.8%. So like totally dominated. Although this is still in theory, we see Higgs, but we cannot really tell how do we actually produce it. So that's the main thing here. Second of all, of course, we could continue with we would have a direct access to the Higgs to fermion like coupling or vertex, and we should be able to understand its like structure, its Lorentz structure. And of course, it's a critical part of the Higgs properties. Having that said, the last remark is that we're glad to be at 13 TV because it's much better than before. Okay, so now coming to TDH is before we try to understand how to do the analysis, we have to understand what should we see in the detector. So first of all, a top quark pair can decay in a bunch of different ways, and there are like three main categories. So in dileptons, so-called decays, leptons plus jets and jets. And then on the Higgs side, we also have another variety of possible final modes. So having this together, we have like study groups. In particular, we have 5 study groups that are actually categorized by the Higgs decays. So we split ourselves depending on the way we expect Higgs to decay. And then subgroups are further like split based on TD bar system. Okay, what's the message here is that the lower we go, approximately, the cleaner is the category. So the less is the noise level drops. However, so does the signal level. So we get better signal-to-noise ratio, but we drastically lose the events that we observe in the detector. Okay, so before going to 13 TV, this is a quick roundup of what happened before, and this table shows different production modes for the Higgs boson, and the measured values with the uncertainties, and we see that the TTH has a pretty, well, it's way behind in the resolution with respect to all other measurements. So that's why we're going to 13 TV now. However, I will not talk in details about every single channel, so every single category that I've just presented. I will focus only on the Higgs decays to BB bar. All right, so how does this look like? First of all, we have a signal and then a background. This is one of the many diagrams, by the way. We have like hundreds of these. And nevertheless, the main challenge in this search is an enormous background, which is this guy. So it's TT bar plus stuff. Most of the time just TT bar plus jets. And in particular, when those jets are B quarks or B jets. And to show you the problem in numbers is that when we talk about the background, we're in hundreds, and if we talk about the signal, we're at like percentile level, so it's like 3 orders of magnitude. Another problem that we have is we don't really see if the jet inside the detector is a B jet, a U jet, a C jet, so any quark. We don't know which quark it is. So we need to apply some techniques to really tell apart, okay, this is a B jet. But these techniques are statistical, they're approximate. So nevertheless, if we take, say, semi-leptonic decays, we end up with the 6 jets here, and we need to do combinatorics to assign which particle came from where. So that's quite some permutations already. Just a brief comment that Atlas and CMS is doing quite similarly on this study. By the way, this result has been removed due to problems they found, but that's not very important right now. Okay, so what's the strategy? How do we do it? So first of all, in this search, we categorize ourselves based on TD bar decays. So we study 2 main categories, lepton plus jets and dileptons. There is a third one, so tops can decay to jets, and that's what we call hadronic decays, so only to jets. Atlas has published the result in the past, but there's no updates, and we're still work in progress. So then we have categories like subcategories. So we take main observables that we like. Those observables are number of jets and number of BTAGs. And then we cluster our events in subcategories. And each subcategory has slightly different performance. All right, and then for each category, so each category is more or less an independent search. So it's quite a standalone search on its own. And once we are there, we could proceed to statistical analysis to get to the bottom of our figures of merit, which are the observed amount of Higgses and the background. Okay, so this is a quick overview of categories that we use in the search. So we have 7 right now, 4 for lepton plus jets, 3 for dilepton channel. And each category, as I've mentioned before, have a dedicated BDT observable, which is boosted decision tree, which is on its own a algorithm, machine learning algorithm. And finally, we use 2 of these multivariate observables. So one that is trained, so one is machine learning based, and the other is theory based. It's called matrix element method discriminant, that we plug into statistical analysis to extract the contents of our data. 2 remarks here is that the more jets we have, the more events we get. But that really makes the detector dirty and difficult to work with all the combinatorics and stuff like that. So I am giving you a couple of slides just to give a quick impression how do these final observables look like. So lepton plus jet category. So blue is the signal multiplied by 15, and different colors are different backgrounds. Similarly, for dilepton category, I picked the best categories just to give you some idea how does it look like. Anyways, I'm jumping to results now, and we see that here we want to hit 1, and results are going to the left with more data, so we're getting close. and the uncertainties on the measured signal are also shrinking. The standard model Higgs lives on 1. Okay, now everything together for ATLAS and CMS. So we see some dancing here. Results are all over the place because the uncertainties are still large. They're shrinking. And standard model Higgs is this solid line. So we have most of the data already published with the data set, with full data set that we have studied so far. And we still have a couple of analyses that are slightly behind. So that's it on my side. I'm going to conclusions. So ATLAS and CMS combination most likely will forbid the background-only hypothesis. Is the Higgs that we see truly the standard model Higgs to be seen? And for individual searches that can answer really the second point, we definitely need more data. And after that, of course, we'll go further into property studies. So thank you for your attention. Questions, please.
So far, statistics is too low to identify the signal.
So error bars tell you about the statistics. It's mostly driven by statistical uncertainty. So yes, it will shrink. And combination will give an answer to that, but then combination will be blind to other important questions. I mean, combination between ATLAS and CMS.
Regarding the popular units of inverse femtobarns, they are basically on fingers number of collisions per area?
It's just number of collisions in general, collected number of collisions.
Per area?
No, just number of collisions.
But femtobarns are...
It's unit of area because it's related to differential cross-section. And differential cross-section is area, so this is inverse area. But effectively, it's just number of collisions.
Dar vieną klausimą prašom, jeigu kas turi.
These zeros that are here, it means just that you didn't find certified events and the uncertainty is really large, which means that as soon as you find some, it moves automatically more to one.
So in the past, I did this analysis, just we were still looking for Higgs at that point. So these guys were very optimistic. They can find this interaction as well. So they did it, but they're just not good at doing this job.
Less likely.
Tai padėkokim dar kartą pranešėjui.